So we finally going to talk about GR's, the field theory of gravitation. Let me remind you that a field theory, any field theory, involves two-step description. You have a source particle and test particle. Uh, the source particle does not act on the test particle through action or distance, but through the creation of field everywhere, and the field then acting on the test particle locally. The equation describes, given the source distribution to find the field, is the field equation. And the equation describes the effect of field on the test particle is the equation of motion. So you're familiar with electromagnetic field, in that case field E and B. So source particle, source charge will create E and B field everywhere through the Maxwell's equation. And the E and B field then act on test particle, test charge through the Lorentz force law, which is the equation of motion for electromagnetism. Now, Einstein theory of gravitation, the field is curved space and time described by the metric g mu nu. And then the source particle will cause the space-time to curve, so you create a curved space and time, and the equation described is the field equation is the Einstein equation. And then a test particle sitting in the curved space-time, its motion is described the geodesic equation. Okay. Now, just make a comment. In pre-GR physics, space and time, including special relativity, is fixed. But in GR now, it is the space-time is dynamical. It's determined by the energy and the energy distribution. It was matter and energy distribution will cause the space-time to curve in different ways. So, the space-time is dynamic quantity. This is an expression of ever-changing relation among physical processes. Now, remember, when the feature around geometry, the geometry is same for all coordinates. It was geometric relation should be invariant under different choices of Gaussian coordinates. So this is compatible with Einstein's belief that space is not a thing, meaning that if you write physics equation, tensor equations, which is unchanged under coordinate transformation. So this is the principle of general covariance because coordinate transformation is general coordinate transformation. This is a key feature of GR. It allows one to find GR equations from symmetry. Remember, we said one way Einstein discovered the GR equations without using experimental crisis is by using the symmetry principle. And GR has the Riemann geometry have just this feature for you to do that. So the geodesic equation we identify as equation of motion for GR. Okay. Remember, equivalent principle says the gravitational equation of motion is totally independent of any property of the test particle. Remember, the cancellation, gravitational inertial mass make the equation just acceleration with the g. This suggests to Einstein that gravitational field, unlike other force field, is related to some fundamental feature of space-time, which he identified the curvature of space-time. Thus, the motion of a particle in the gravitational field is the same as a free particle in a curved space-time. Okay. Because it's not due to force, but it's just the underlying space-time tells how a particle moves. So in some sense, it's a free particle. This naturally suggests that gravitational equation of motion is given by the geodesic equation, because geodesic equation is the curve describes the shortest and straightest possible curve. It's a free particle. So this, some says, a heuristic suggestion that equation motion is geodesic equation would be supported by a more formal derivation where we have to know how to do the tensor analysis in general relativity. So the takeaways for lecture number 11. First, remember we made a geometric derivation of the geodesic equation as an example how the metric fixes the geometric relations in the space. And this is the geodesic equation which the second derivative of position is related to something gamma, which is first derivative of the metric. Then we derive this through the calculation of variation from the principle of least action. So we review those topics and see how the geodesic equation can derive this way. And then we talked about the geometric theory in physics. We learned from equivalent principle of physics of time dilation. We can view the gravitational field as modeled by a curved space and time. So the gravity changes from g0 to -1 to this position dependent function. And also we point out such a metric theory automatically incorporates equivalent principle because through the flatness theorem of curves space. And GR is a field equation gravity, with field being the curved space and time. It's a two-step description involving field, and the GR space and time is dynamical. Okay? It depends on determined by the matter and the energy distribution. Next lecture, we're going to talk more about the geodesic equation as equation motion. We'll show that it reduces in the Newtonian limit to the equation motion of Newton theory. Okay, so this is really the purpose of this derivation, to show what limit allows the geodesic equation to be derived to be reduced down to Newton's equation motion. So this clarifies the precise relation between the Newton theory and Einstein theory. The Newtonian limit of Einstein theory reduced Newton theory. And also we're going to, in fact, start in chapter 6, start search for GR field equations. And this involves a short introduction of curvature, which is second derivative of the metric.